Okay, everyone, we're recording. 2.8 continued. All right, very good. Okay, let's define a basis. So we know what a subspace is. What's a basis? So here's the formal definition, and I'll unpack that a little bit more. So, all right, so a basis, that's the thing we're defining, is a linearly independent set that spans the subspace H. Basis is a linearly independent set that spans the subspace H. There are two big qualifiers to be a basis. One, the set's got to be linearly independent. And two, it's got to span the whole subspace that we're talking about, okay? A really nice kind of phrase to describe a basis is this: a minimally spanning set. A minimally spanning set. So let's think about it in the easy spaces that we like to live for our initial examples. Let's think about this in R3, okay? And let's think about a 2D subspace of R3. So you know that that means a plane through the origin. So a minimally spanning set for a plane through the origin is just any two linearly independent vectors that lie in that plane. So like we could say that the subspace H is the span of, let's make up three vectors. We could say 1, 0, -2, 3, 1, 5. And now I'm going to make the last vector a linear combination of the first two. So I'm going to make it 4, 1, 3. It's just the sum of the first two vectors. Because this is just a 2D subspace of R3, we don't need all three vectors, right? This one was created from the other two, so it's not needed. So the basis for this subspace would be 1, 0, -2, and 3, 1, 5, because it's the smallest possible set that we could construct that still spans the plane that we need.
Does it matter which of those you chose?
Nope. We could take the first and the third. And yeah, in this case, it doesn't matter, but there are cases where it would matter, right? You could have two vectors that only lie on a line, and then the other one is the one that's needed to span the space.
So it just has to fall within the span of H, not span all of H?
What do you mean? What? When you say it, what do you mean?
Like the basis,
The basis, the two basis vectors have to span all of H.
span all of it.
So in other words, we should be able to generate the subspace using just those two
Oh,
vectors.
okay.
Okay.
So you can only get a basis if it's from a linear independent like set of right?
You can, yeah, you could have a big set of vectors, and out of those, you need a basis would be two that are linearly independent, or three that are linearly independent if we're in a higher space. Okay. All right, so the standard basis that we use all the time, and you've actually used this since we started doing coordinate stuff whenever in 6th grade or 5th grade. So the standard basis for Rn is the set E1, E2, E3, all the way out to En. You remember what those E's mean?
They are vectors.
Yes.
They're the unit vector
Yeah.
in that.
Louder.
The unit vector in each new dimension.
They're the unit vector in each new dimension. They are the columns of the identity. These are the columns of the n by n identity. So they're the columns of I sub n. So E1 is, 1, 0, 0, blah, 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 blah. E2 is 0, 1, 0, blah, blah, blah. This set is going to span all of Rn. So that's the basis that we most frequently use. And when we're in small dimensions, we call it I, J, and K. And in fact, the columns of any invertible matrix form a basis for Rn. I want to talk about why that's true. The columns of any invertible matrix form a basis for Rn. Why? Why is this okay to say? Yeah.
Yeah, all invertible matrices go down to the identity.
Say that in a more precise language.
Be reft down to the identity.
Good job. All invertible matrices can be bereft to the identity. Well, how do you know that?
Because they're all linearly independent.
All you have to do is cite a theorem. The big theorem, that's right, the invertible matrix theorem, right? So every invertible matrix can be bereft to the identity. So that means that every invertible matrix contains n linearly independent vectors, right? If it's invertible, it's n by n. It's a square. So the vectors are linearly independent, and they're also going to span all of Rn. So we've got the two conditions needed for being a basis, right? What were the two conditions? They have to be linearly independent. Yep. If it's invertible, they're linearly independent columns, and it has to span the subspace. Well, to span Rn, you need n linearly independent vectors, which you get if you have an invertible matrix. Okay, we're recording again. All right, so 15, the answer was yes, they form a basis. Are you seeing what I'm writing on the board, you guys? Yes, okay. And 16 is no, they don't form a basis. And that's because they are linearly dependent, because they are scalar multiples of each other. Okay, I'm gonna do one more and then I'll have you guys do the rest of the set tonight for homework, or wait, no, not tonight, Sunday night for homework. Okay, so 17 says these three vectors, 0, 1, -2, 5, -7, 4, and 6, 3, 5. The question is, are those a basis for R3?
On the surface, it appears
Can we,
so, but
can you see anything? Because you seem to be good at seeing things just with your eyes.
yeah, they don't look like scalar multiples.
He's got the shotgun.
No, good about, well, they're certainly not scalar multiples, but do you see any linear combination?
No.
I don't.
Yeah,
Does anybody online see something without doing any work?
I'm asking TI.
I think we should have you ref this by hand.
All right, let's not ref by hand. Let's actually use TI. Oh, I discovered the other day a matrix calculator on Desmos. Did you guys know that exists? It's kind of cool. I'll show you in a second. So type this in 0, 5, 6, 1, -7, 3, and -2, 4, 5. What's the answer then? It refers to the identity. So yes, it's a basis. So yes, ref gives us the 3 by 3 identity. Okay, so that's how we determine if something's a basis or not. We've answered the question of what is a basis and how do you find one in general. Okay. The other things on my bullet list were how do you find one for a null space and how do you find one for a column space? Okay, I'm gonna put somebody on the spot. In person or at home? What do you think?
At home.
In person. Maria, what is the null space? Don't look it up. Just see if you can.
The solution to like AX equals 0.
Beautiful. Well said. Okay, so here's a reminder of what null A is. Null A is the set of solutions, what Maria just said. Set of solutions to AX equals 0. Okay, if A is an M by N, right? A is always an M by N in our world. Let's put David on the spot. David, the null space is a subspace of what larger vector space? Rn. Nancy or Mary? Nancy. Beautiful. Well done. So all the X's are elements of Rn. So the null space is a subspace of Rn. It's going to be some bunch of vectors in Rn. Now, how do we find a basis for this thing? Let's start with an example, okay? So finding a basis. Here is the matrix A that we're going to tackle. It's a big one. -3, 6, -1, 1, -7, 1, -2, 2, 3, -1, 2, -4, 5, 8, -4.
Why finding a basis is more complicated than just removing it.
Say that again. You're confused why finding a basis.
Why is it any different from just bereffing than finding, like, if you solve for if it's linear independent or independent, then can't you just like beref it and then find a solution?
That's exactly how you do find a basis.
Okay.
Yep.
So like,
So the work
Okay.
that we did in learning what parametric vector form is exactly the work we do to find a basis. So what we're after here is we're after the vectors x1, x2, you know, a vector that looks like this. Oh, wait, here's a good question. How big should that vector be right there? That 0 vector?
it would be,
A 1 by 5.
Nope,
would it be
Five
if you
by
were right?
five. Oh.
3 by 1.
Is the top, is that a -7 on the top?
-7, yeah. So this, right, because what would we be doing? We'd be taking a scalar weight on this column and a scalar weight on this column all the way across, and we're gonna get a 3 by 1. So we're solving this, right? And we know to solve this by rereffing. And when we solve it, that's gonna tell us what all the solutions are. And then what's cool is that the basis is literally that finite set of vectors. So let's go through this. It's a 3 by 6, right? So -3, 6, -1, 1, -7, 0. 1, -2, 2, 3, -1, 0. 2, -4, 5, 8, -4, 0. Okay. I think many of you take pretty careful notes, so if you want to write this down, I'll pause and let you have time to do that. That's what it becomes.
And this one's augmented, right?
That's augmented, yeah. So we could put the dashed lines in there if we want. Ignore the little RP at the bottom. I was doing attendance and I typed it in the wrong sheet. You guys know what RP stands for?
Present remote.
Really
Remote
present.
Removed present.
Real.
You know, ordinarily.
Really fast.
Real person.
real person.
It took up the room.
Okay, so let's write the solution. Ready? I was a little upset that when I gave the verbal exam, some people didn't know how to do this. So can we make sure we're solid on this? The free variables here are x2 and x4 and x5, which means that all of the other variables can be written in terms of those. So x1 is 2x2 plus x4 minus x5. Yeah, thank you. That's what I meant.
Gosh.
X2, I know, I'm terrible. X2 is x2. X3 is negative 2x4 plus 2x5. X4 is free and x5 is free. Anybody have any advice for how I could teach this better the first time around so it sticks? Like how to do parametric vector form?
I just don't know where it was called.
Oh.
Parametric.
Like now that you've seen it so many times, is there something particularly confusing about the way I first introduced it that you could improve on? Okay.
Yeah, I don't really remember how we first were introduced to it. I just like kind of just memorized what the steps are. Like
Okay.
I don't remember how it's.
I don't know what they're called.
Wait, do you feel like this course has been a lot of memorization?
No,
I think
feel
it's-
like a lot of it is like, I understand it, but like trying to like apply it is like, it's like harder to apply, like in multivariable, like if I understood it visually, it's easy to apply, but here's like, I can understand it visually, but like when I try to do the math, it's just like.
I think it's a lot of like familiarizing yourself with vocab,
Mhm.
because like the math itself, when you said this at the beginning of the semester, it really isn't that hard. It actually hasn't changed that much.
Mhm.
It's just kind of, you have to kind of, this is something that I feel like you would like, a college course, like it's when you would more read out of a textbook, because there is a lot of vocab,
Mhm.
not necessarily memorizing it, but like just understanding what it means.
How do you think we could become better familiar with the vocab?
Do you want to make a vocab sheet?
I mean, what did you say?
I just said vocab list.
Oh,
No test.
just like definitions. Yeah.
Not definitions, but I just like, I don't think we do a lot of, we just do it and that's how I memorize it, but,
Yeah.
and I
I
know how
think-
to do, I just don't, like, but when you say like parametric vector form, I, like, this doesn't pop up.
All right,
Oh.
cool, hear me out. At the end of the
I'm
year,
listening.
we get in groups. No, this is our final. We get in groups and then we each make a vocab sheet for each unit. So kind of like a cheat sheet for each thing. So this is
Mm.
parametric vector form. This is matrix
Mhm.
forms.
Mhm.
Like just kind of each of those things, even though like the math, you'll like
Mhm.
say this, but like you could say this is how you find null A. This is how you find
Yeah, like a big, like,
all A.
yeah, like a collaboratively created review kind of.
And then you could use it next year.
It's true. It's true. Okay.
Oh.
Well, thanks for the thoughts. Oops, there goes the remote. Okay, so here's what it looks like in parametric vector form. X2 times all the coefficients of X2. 2, 1, 0, 0, 0. And X4 times all the coefficients of X4. 1, 0, negative 2, 1, 0. And X5 times negative 3, 0, 2, 0, 1. This, okay, I gotta be really explicit about this next thing I say. This thing right here is the null space. This is null A. Another way of saying that would be to say that this is the solution set to AX equals 0. But it's not a basis yet, right? We have to confirm that this set is linearly independent. The cool thing is, though, that they always are. By the way this set is constructed, it's a linearly independent set. Okay, I want to actually read a blurb straight out of the textbook to explain why that's true.
Put equals 0 vector, right?
No, we would not put equals a 0 vector there. The only thing we would add to that would we could say equals x1, x2, x3, x4, x5. But
Okay.
that's not equal to the 0 vector. So listen to this sentence, okay? this construction of UVW, which we just got, those are the vectors UV and W, okay, automatically makes them linearly independent because equation 1 shows that, and I'll show you what equation 1 is in just a second. Equation 1 shows that 0 equals x2u plus x4v plus x5w only if the weights are all 0. Okay, examine entries in 2, 4, and 5. So if you were to put, let me state the basis and then try and unpack that a little more. The basis of the null space is just the finite set of vectors. This one and only that one, not all the linear combinations of it. And this one. And this one. I think I might have an analogy coming to mind that might help. So write that down and then I want to share this analogy and you can tell me if you like it or not.
So what is the basis?
Okay, someone tell her that. What does the basis mean again?
Linearly independent set that spans a subset H or subspace H.
Okay, can you say it in less formal language?
It's the same as whatever subspace you are, but I guess it's just with all the redundant vectors cut out of it.
Okay, I like that. You said redundant vectors. Can you add something?
It's just two vectors that can make any vector in the subspace H.
It's you're close. In this case, there's 3, but yeah. Yeah,
Well,
so it's like the minimum building blocks for the entire subspace. Okay,
And
Like-
there's only one answer to that?
or is there only one answer
Like
to
one
the basis?
yeah. Or
No,
are there
there could be
multiple?
multiple answers. Yeah. Like these building blocks could make the subspace, but we could generate other building blocks that would too. The key though is that they have to be linearly independent.
But in this case, there would always have to be 3.
Yes.
Could you
How
use
do you know the
any,
smallest?
if you use any 3 linearly independent vectors in the subspace?
Yes. As long as they're actually in the subspace, right? So as long as, you could fix these numbers to be something and then generate vectors in the space. And as long as that set is linearly independent, it will count as a basis. So how do you know how many are in the basis? It's the number of free variables, right? Because the number of free variables dictates the number of vectors that we're going to have here. And this set is linearly independent automatically by how we constructed it.
So if A is an n by n matrix, will the basis always be an n by m matrix?
The basis is a finite set of vectors. It's not really a matrix. And so the basis for a null space is going to always be the number of free variables. Zoom people, do you have any questions?
And it always is just those numbers, those vectors that come out.
Those vectors that come out of that process of solving that we've been doing all year. That's the basis. Okay. The analogy I was going to make was to factoring numbers. The reason this is on my mind is because I'm teaching algebra studies how to factor today. And so this is just a quick aside. I don't know if this helps you or not. Think about what a basis is. So think about the number 24, okay? So 24 can be written as 1 times 24 or 2 times 12 or 3 times 8 or 4 times 6. Did I do them all?
5 times 5 minus 1.
Stop.
Got 'em.
Okay, that's all of them, right? So you could say in a way that like the building blocks of 24 are this list of numbers, 1, 2, 3, 4, 6, 8, 12, and 24. Those are the building blocks, but what do we actually need to build 24? Like what are the bare bones things to build 24? 2 times 2 times 2 times 3. Do you get what I'm saying? It's like these things are members of the set of factors of 24, right? But these are the prime factors, right? So these are the things that they're like the smallest possible building set to make 24. I don't know if that helps you at all, but it's the set of like, yeah, there's infinitely many vectors in this set. In the set that I have in the red box, there's infinitely many vectors in this set, but we only need 3 to generate everything else.
Well, there was like this, I think someone solved it now, but there was like some theory about like where like prime numbers stop. Because like there's theory that if you keep on going for infinite, are there like infinite sets of prime numbers, or do the prime numbers stop somewhere? And I think someone solved it. I'm not sure.
That's a well-known thing in math. Yeah, they solve. It is. There are infinitely many primes.
No way.
Yeah.
It's
It's been proved. I can't remember what the name of the proof is, but you've got your phone out. Can you Google it?
Yeah.
Proof of infinitely many primes. Okay, so we've shown how to find the basis of a null space. What is it called? Euclid's theorem. Wow, that's got to be important because Euclid did a lot. So, okay. Let's find the column space now. Let's find the basis for a column space. Okay. All right, so let's take a matrix. This will be example number whatever. I don't know. Here's matrix B now. All right, so it's 1, 0, -3, 5, 0. It's going to be in ref form already. Okay, so if you're, so we've got that and we've got that.
Theorem section.
Okay, that's our matrix, and it's not augmented, so don't get panicky about that 1 on the end. Okay, this should be a question that you can answer quickly without any work or thought. Ready? No thinking. Does this set of vectors span all of our 4?
No.
Right? Because we don't have a pivot in every. Nope, that makes it linearly dependent row, right? We don't have a pivot in every row, okay? Which is kind of obvious, right? Like clearly you can't make anything meaningful out of this last spot. See, it's not going to span all of our 4, right? Right away we know that. Okay, so we could say this based on what we see right here. Couldn't we say that this column is a linear combination of those two? And that column is a linear combination of those two, but this one is special. Okay, so let's note that. So B1, the first column, is equal to -3. Oh no, I'm lying. I'm writing that wrong. Sorry. B3 is equal to -3 B1 plus 5. No, plus 2 B2. The third column is -3 copies of B1 plus 2 copies of B2. And B4 is equal to 5 copies of B1 minus 1 copy of B2. Okay, well, what does it mean to be in the column space of B?
It's within the span of the columns.
Okay, well said.
Linear combinations of the columns.
Well said. So any vector V can be written, any vector V in col B, right? Any vector V in the column space can be written as V equals C1 B1 plus C2 B2 plus C3 B3 plus C4 B4 plus C5 B5, right? And that's what Hugh just said. Any vector in the column space can be written as a linear combination of the columns of B.
Is that part of the theorem that I just showed?
I think. I'm not sure. What are you referring to?
Like the 3 rules that determine if a vector is.
If you have a subspace?
Yeah.
No, this is not related to that. Okay, so we know that, right? Any vector in the column space can be written as a linear combination of the columns. But actually, look what we have. We can sub some stuff, can't we? Because of this thing that we observed, right? This thing, this statement here, can go in place of B3, thereby eliminating B3. And this thing right here can go in place of B4, thereby eliminating B4. So what does this mean? But actually, we can sub and show that any V in col B can be written in terms of V1 B1, B2, and B5. which are the pivot columns of B. Now, the pivot columns are automatically linearly independent, aren't they? You've got a 1 there, you've got the step down nature of echelon form, right? A 1, a 1, and a 1. The pivot columns are automatically linearly independent. And so this is interesting that we've got 5 columns, only 3 of them are pivots, and the basis has 3 vectors. So the basis for the column space is just the pivot columns of the matrix. But is it the pivot columns of the ref form or the pivot columns of the original? It's the pivot columns of the original. Okay, so here's why that's true. Suppose both AX equals 0 and BX equals 0. And B is just the ref of A. Okay, suppose both AX equals 0 and BX equals 0, and B is just the ref of A. Well, the same relationship that exists among the columns of B, the ref form, also exists among the columns of A, right? When 2 matrices are row equivalent, that means that they have the same solution set, right? So if these have the same solution set, these 2 have the same solution set, then whatever relationship exists among the columns exists among both of those. So if we were to make this other matrix, so this matrix is going to be the non-ref form of the one we just looked at. They have the same solution set, then they have the same relationship among the columns. There's the same like linear dependence relation that can be written among the columns. This matrix that I just drew, this is just the non-ref of the matrix B that we saw before. Okay, so let's make some connections. You look like you're still writing. Yes, to your question, Izzy. The set B1, B2, B5 is the basis for call A. Okay, check this out. So I want to go to the calculator and I want to ref the matrix that we just wrote down. How big is it? 3 by 5? You will call me out if I make a mistake. You didn't. Turds. There we go.
How did you see that?
Oh, this little button right there.
What's that?
That little like return button, it will create a new row for you.
Ooh,
Nice, huh?
yeah. Oh,
You got
so
extra
is there
columns
another,
the same
is
way
there a
too,
trick
or-
for a column?
Yeah, there's a trick for a column. You just do shift return. Oh, sorry guys. I should have taught that a long time ago. I'm sorry. That is nice, isn't it?
Oh my god.
Okay, look at this. This thing should look familiar. This is B. This is A. So B is just the ref form of A.
and wait, they're row equivalent, which means they have the same solution set, which means whatever relationship exists among these columns also exists among these columns. So see what we built? We can see this one obviously, right? This column is -3 times this one plus 2 times this one. We can't see it as obviously here, but it's still true. Watch. -3 times this column, which is -3, plus 2 times this column, which is 6. What's -3 plus 6? It works. Let's try one more time. What's -3 times -2? 6 plus -2 times 2. 4. -4. 6 plus -4 makes 2. So it's working, right? And the same thing's going to be true over here. The fourth column is 5 times this one plus -1 times that, but you can do it real quick. 5 minus 3 does make 2. -10 plus 2 makes -8. It works. Okay, so what does this mean? Izzy, your comment actually makes the conclusion that we're about to write. Okay, so here is the way to find the basis for a column space. This is a theorem. The pivot columns of a matrix A, the pivot columns of a matrix A form a basis for the column space of A. Which means in this case, call A basis is, let's just use letters. Let's not write them out. The basis for call A is A1, A2, and A5. Okay, all that theory, all that discussion, all that building up leads us to, okay, Mr. Cope asks for a basis for the column space. You ref, you see which columns are pivot, and you go back to your original matrix and name those columns as your basis. That's it.
Can we write down the steps?
Sure. So 1, leave a ref. 2, see which columns are pivot.
Do you want the one step?
Yep. 3, go back to the original matrix. And name or list, maybe we should say, and list those columns. As basis.
So in the previous problem, we found the basis of the null space, not the column space.
Correct.
Okay.
You see a bit of a connection, right? That here, well, disconnection maybe. Here we're looking at the pivot columns. In the other case, we're looking at the non-pivots. We were concerned about free variables.
Right.
Yeah.
That's what I was.
Yeah, that's
So
Yeah.
that's the difference between column, finding column space and null space.
yeah. So finding null space really means we're refing and then writing in parametric vector form and developing them that way. In this case, it's for refing, but we don't really care about what we get. We just care about which columns are pivot. So we're not,
Yeah.
when we ref for a column space, we're not actually solving it. We're just taking the column.
You're getting the actual column.
You're getting the columns. And I want you to remind tonight, it's really important. It's the columns of the original matrix, not the columns of the bereft one. Because if we took the columns of the bereft one, it would always be 1, 0, 0, 1, and there wouldn't be an actual subspace that we're interested in. Zoom people, questions? Okay. Well, we're at an awkward place and we have 8 minutes left.
We didn't have a discussion about questions
No, I'm doing work. I want to do work.
in 8 minutes.
What we'll do.
I guess I really overplanned, didn't I?
Well.
Yeah, let's do the homework together.
Hey.
Can we do that? Can we just do some problems? Okay, so we'll do 2-9 next time. So 15 through 20, I did a few already. Let's finish them up. And yeah, it's a good idea. You guys at home have your books, please go to page 153. And you guys in the room, I'll just write them on the board since I know you probably don't have books. What did we do so far? We did 15. We did up to 17 and I've assigned up through 20. So let's do 18. Okay, 18. Here's the list of vectors. 1, 1, -2, -5, 1, 2, and 7, 0, -5. Remember, the question here is it a basis for R3? Can anybody spot a relationship? I can't spot a relationship, right? I don't see that any of them are like scalar multiples or anything, so we'll go ahead and ref it. Okay, our conclusion then, since it refs to the identity, is yes, it is a basis. Yes, because ref gives us the 3x3 identity. Okay, I love the next two because they're quick and easy. This really gets at, do you understand the two qualifications needed for a basis? Let's review them again. Linearly independent and must span whatever space we're talking about, right? So linearly independent and span it. Okay, so here's what they give us for 19. They give us 3, -8, 1, and they give us 6, 2, -5. So the question is still, is it a basis for R3? How can you tell so fast?
You can't span R3 vectors.
Good job. No, can't span R3 with 2 vectors.
I love like learning about like basics of like space.
I mean,
Can't cover 3 dimensions with only 2 vectors. It seems really straightforward,
Yeah.
but it's like weird.
Yeah.
The whole course.
here, let's save us some time. Ready? Who wants to write out 12 numbers? In number 20, they give us 4 vectors in R3.
Spans R3.
Is it a basis?
No, because it's
No,
not the
it's
most
not
simple.
linearly independent.
Say what you were saying?
Two of them have to be redundant.
Yeah, something's got to be redundant. No, maybe not 2, just 1. Yeah, right. Something's going to be redundant. You cannot have a set of 4 vectors in R3 and be linearly independent. So the answer is no, not a basis. And the reason is too many vectors.
Redundant is a good word.
Yeah, redundant is a good word for that. There, it's really, it doesn't, in other words, it doesn't add anything to the building blocks, basically. Okay, next I assigned number 25 and then 27 through 29. 25. Okay. All right, this case, it says that it gives you a matrix. It's a fairly large one, so I don't know, you might, if you're tired of writing, just feel free to stop and you can just think through this with me. So there's the matrix they give us. The directions are, by the way, so it says they're giving us a matrix A, and then they also give us an echelon form of A. So they also tell us they've like done the calculator work for us. Unfortunately, they don't put it in ref, but that's okay because we can still tell what the pivots are. The scribble, what's that called? Come on, you know the name.
I do.
Or someone in Spanish class does.
Oh, that's the.
The tilde. The tilde, yep. The tilde means is row equivalent to.
Oh,
Row equivalent means, right, that we can reach one from the other by using the elementary row operations. Okay, so this is what they state in the text. And they ask for, they say, find a basis for call A and a basis for null A.
A1, A2, A4.
Mhm. See the pivots? The pivots are here, here, and here. So a basis for call A is A1, A2, and A4. So does call A span all of our four? No. Remember the video last time? We were having fun with the statement full rank. This is not full rank, right? Because the vectors are in R4, but it doesn't span all of R4. What's the rank here? It's rank 3. That's right. Okay, so the basis for call A is that. Now, it's a little more work to find a basis for null A, isn't it? We would want that in reduced row echelon form, not just row echelon form. Okay, so, but you could technically do it as long as you're careful to, yeah, no, I guess it's probably just easier if you row ref, right? Are we done? Is it 3:13.5? Okay, I'm gonna stop the recording. I'll post it later.